design for manufacturability is an important area in device fabrication, circuit fabrication, and getting the right yield and desired performance that you want. So design for manufacturability is a broad area, as we already saw in the last lecture. So in this section, what I would like you to do is to go through one unit process to look at how design for manufacturability could be implemented while you are designing or while you are developing a process, right? So let's look at how one can look at this process and why DFM is important, right? So what are all the goals of DFM? So design for manufacturability or technology aware design is to increase the yield. So that's a primary goal. So we want to increase the yield and also reliability of the fabricated device or circuits. So it is important to understand, we want to make sure your device is reliable and also your yield is high, so that you can get many devices out of one process step, right? So whatever process that we do is going to be a reliability concern, and also all the material that we use is also a reliability concern. So when we say each step, so processing required multiple steps, right? So we saw for example, for patterning you need optical lithography followed by, let's say, dry etching. So optical lithography involves photoresist, illumination, development, and so on. And dry etching requires exposure of your material to plasma, right? And for instance, if you want to fill a gap, you want to deposit dielectric material, let's say silicon dioxide. So the process step and also material that you use, in this case for instance silicon dioxide, what is the reliability of that particular oxide over time, whether my oxide dielectric constant is going to change over time, right? So those are all potential concern, and one need to be aware of quality of oxide and the quality of material in general, and the quality of each and every step is maintained, right? So if you want to achieve high yield and reliability, we should understand the unit process, right? So what is the effect of unit process and the integration process as well, so that we can address the manufacturing problems. So if there is a unit process failure, so we should be able to understand what is the implication of that failure, or if the integration process fail between two different steps, we should be able to understand what is the reliability and yield implications of that, so that we could design our circuits in order to accommodate for such deviation from optimal process. So how do we do that? So we can either take fabrication process details, a complete detail on fabrication process, right? Or you use DFM tools. There are tools available these days integrated in design flow itself, and then use those tools to identify and fix issues in your design. Okay. So as I mentioned earlier in the previous lecture, fabrication process details may or may not be fully shared with the designer. However, when you are using a PDK, so that has encrypted data that one can use, so that you understand the corners and so on. And we can also use simulators, right? So you can do simulators to understand potential failure. So we will look at what kind of simulators and how you can do that. I'm taking here lithography as an example, right, as a unit example process. So when you take lithography, you can do lithography simulators, right? So there are multiple simulators available. Some are proprietary, some are open source based on the complexity that you have in your circuitry. And then when you run these simulator on your design, right? So if you make a certain design, and then we will run through the simulator. So you have the simulator, and then we want to see what will be my image on the photoresist. So it might be something like this, right? So we want to understand what is the effect of the edges, what is the effect of corner, and then use this to understand the parametric related problems, right. So if you are doing some sort of high speed circuit, then you may want to understand how my speed is going to be limited by this. And if you are designing much more complex logic circuit with memory and so on, what is my memory requirement if I am going to have suboptimal operation because of my lithography limitation. So by understanding this, you should be able to design circuits in a better performing metric. So as I mentioned earlier, most of the EDA tools these days give you opportunity to do physical model simulation, and by doing those simulations, we should be able to actually extract timing issues, right. If you are doing a digital design and if you want to synchronize multiple blocks with a synchronized clock, you may want to have the clocks aligned without any delay between the different blocks. And if one block is relatively slower than the other, and you might miss the timing, and then whole of your logic is going to be not met requirement, right. So here you want to understand whether my timing will be affected because of the physical design I have, or what is the margin I have. So all those things could be done using present day design tools. And when we say litho process simulation, this could be related to optical proximity correction, right. So if you have a line close to the particular structure that you want to have a certain clearance between these two, and also you want to look at these edge effects. So we can run optical proximity model on this particular design that you have, and the model will tell you where to add features, reduce features to counter your proximity related issues. And physical model, as I mentioned, can be used as well, and then you can do a complete projection lithography simulation as well. Your proximity is much more refined, but the projection optical simulation is to give you how your line widths are going to vary, whether it is widening or narrowing. All those effects could be extracted from projection simulation. So once you get this simulation done, then you will be in a better shape. You will have enough information to go back to your design and correct those design. And in advanced tools, actually you can extract all these defect points, or points where you can locations that you need to attend to, right. For instance, if there is a very narrow gap, and post simulation you find out that this gap would merge, right, creating a short circuit. So if this is the case, you will go back to your design, and then if earlier design was 100 nanometer gap, perhaps you will increase this to 110 or above, right, based on how much overlap you had from your simulation. So by doing this, you are making the circuits more robust to unit process variation or limitation, and also you are increasing yield, right. So you are increasing yield of this particular circuit or particular device. So in both the ways, you get better manufacturing capability when you go into the details of each and every hotspots. So what you get out of this is a design rule. So at the end of the day, you want a lithography friendly design, right. So how we achieve this? The first point in achieving a litho friendly design is following DRC, right, design rule compliance, right. So design rule check is the first step. So if you clear design rule, then you presume that all your devices will be on spec and you don't have to worry about your yield and so on. But that may not be true. Physically, there are certain limitations, right, and that will that was used to define this DRC. So these are all the two instances that can be used in order to make your lithography friendly to your design, right. So one is you define a wide range of design variation, right, with optimized yield. So what do we mean by wide range of design variation? So the process itself will allow you multiple pitch or variation, right. So let's say I have 3 different pitch, right. So this is pitch 1, pitch 2 and pitch 3. So you can have similarly till pitch 4 and 5, let's say. So now my process allows all of this to be fabricated with one single lithography process, right. So this gives you wide range of design that you can use for your complex circuit, right. So you are very happy as a designer because now you are not restricted with one gap or one line width. So you have multiple line widths and gaps that you can use. So as a designer you are happy, but then the problem here is your lithography may not be optimum for all the 5 pitch or designs that you have. Probably it was optimized for P3, let's say, while the window was achieved between P4 and P5. Let's say the window here is plus minus 10%, right. But then when you are designing, you presume whatever pitch that was given to you that is available, you presume that all these pitches are optimal, right. That may not be true, right. So that is very important when your design has multiple variation, and also if the lithography process also tells you that you can print all these different variation, then you should be a little more cautious about what is the yield on each of this design or each of this pitch, right. If they are suboptimal, then you may want to rethink about your complexity. You don't want the circuit to be relying on the really narrow process window for individual pitches, right, while there is a global overlap. So you need to be very careful about that. It might be very attractive just to look at, there are wide range of design you can fabricate, but whether all of them will yield to your requirement is a question, and that should be clarified. And the next way to improve your yield is by restricting the number of designs that is allowed. So instead of 5 design, I will allow only 2. P1 and P2 are only the 2 designs that is allowed, and this will actually give you maximum yield because there are only 2 structures that I am allowed, right. So if the pitch P1 and pitch P2, right. So this is P1 pitch and then P2 pitch, right. So only these 2 are allowed, right. And if this is the case, then I expect very tighter control of variation, right, for P1 and P2. So this might be little difficult for some of the designers, right, where they want variety, but this will give you high yield and reliability. So there is both advantage and disadvantage in going for a large number of variety. At the same time, circuits are complex. So there is a critical point that if you can't yield all the variation, your final circuitry might not perform optimal. On the other hand, we restrict the available design, right. So we restrict to 1 or 2. That will put pressure on the designer that you have to comply to only these 2 variation, but then your yield is going to be high. So is your reliability. So there is always a trade-off between these 2, and it's up to the designer to choose what kind of rule you want to use or what kind of design you want to use, right, in order to yield better circuits. And there is a difference in using the classical design rule and the restricted design rule. So when we say restricted design rule, this is the follow up of what we just discussed earlier, right? So to restrict yourself to certain configuration where the yield is going to be high. In a classic design, it's a very simple scaling strategy, right? But you can use optimum area in order to do this, because the design variations are high, and then you can identify and fix the issues, right? It's not that you cannot fix issues. You can fix the issues, but then this might result in yield issues, right? So you have to identify each and every hotspots, and then you fix it, and whether the fixing is going to be optimal or not is again a question, and the area that you can use is also going to be restricted, right? So you can use pretty large areas here, because the classical design doesn't really restrict you to use only a certain footprint, because the scaling is very easy, because if you use 5 designs and then each one of this design is yielding at certain percentage, then you should be able to apply these designs all over your circuit. So you should not worry about that. And the next thing is about restricted design. So what do we mean by restricted design? So this involves restricted scaling. So you cannot increase your density, or you may not be able to play with multiple dimensions, right, that freely. So there is a restriction given to that. And there is a problem with area as well. So since you are restricting, you want to have higher yield, so this high yield could be only guaranteed for a certain area, right? So you won't be able to scale this independent of your rule or your yield that you are looking for. So all the yield numbers that you get out of this DRC is only for restricted to certain area. And once you do all of this, you get a very good litho friendly layout. So this is very important. So once you have litho friendly layout, then you are guaranteed that the output is, or your device is going to be yielding with a higher percentage and reliable as well. So this is just an example of how one can do litho aware design. On the left side is just a stick diagram of the design. On the right side is the layout, right? So I have here 4 transistors with varying length and width, right? So gate length and gate width I'm trying to vary, all right. But then how do we do this in the layout? So here I have the gate, the central channel, and then you are going to have various gate width and gate length, okay. So now this is all defined as a rectangle, right? So this is how you will also do in your layout. But if we fabricate this, we know that we cannot have very sharp transitions, right? So it is going to give something like this. So here if you look at the designs here, let me draw this one, right? It's not really nice on this part. So you take this, you have varying widths, right? And then you also have something like this, right? So these corners are going to be the trouble points, right? So these corners that are actually very sharp is not going to be sharp anymore. It's going to be blunt, right? And now you have a certain width and certain length. And now your effective length and width is going to be very different. So your effective width and your length is going to be very different, right? Because of this rounding. So one need to be careful about what you have on the layout and also on your design, how to avoid these kind of rounding so that you can get effectively L1 L2 by modifying these design, right? And this is also true if you want to connect this to another line, right? And if it is ending here, this is also going to be rounded, right? So you will have rounding here, rounding here, rounding here, and so on, right? So what is the effective length of these is again a question mark, right? So if you understand the process, if we understand the rounding, right, from whatever you want, and this will help you to design your layout in a proper fashion, because whatever you design or put it in the layout may not result in what you are looking for. Okay, so this is what we call layout aware design. Okay, so you are not just like that dropping in your gate here, but you know how it is going to get fabricated and how this is going to yield as a circuit, and then you can come back to your layout and then you will fix this issue. Okay. So this is the general design flow. First you start with the design and then you run design rule check, right? This is very standard procedure that you look for any violation of design. For instance, if you are designing in 130 nanometer node, and then if your structures are 100 nanometers or below 100 nanometers, then your design rule check is going to be negative, right? So if my structures are 100, then there will be a design violation. So then they will say that you are not allowed to design anything below 130 nanometer. So this is what helps you to refine your design. Okay, so once you are DRC clean, right? So design rule is all clean, then you go to layout, right? So next you do the layouting, right? How the transistors should be fabricated, how they are connected. So all those things you will do. And in this layout, and then the schematic need to be checked. So this is again an important step, right? Whether all your connectivities are properly done, right? If there are any shorts and if there are any open, right? The places where it should be start, is it open, right? There are some regions that could overlap with the other, right? All those things will be checked in this. And while you are doing all these refinement, right, you also send the layout parametric data as well, right? So after designing, the first step is you extract the parameters, right? This is a functional parameter. So I design this particular circuit for a certain functionality, right? For instance, I design a digital circuit that will do something, but then there are synchronization data, right? There are timing data between different blocks. So all those parametric details are collected, right, and used for later use, right? So that is what your intention, right? So this is intention where intended application should be very clear. So after looking at layout, the next thing is to do proximity correction, right? So now the layout is done, and the next is goes to proximity correction, and this is where you are going to do some simulation of how this is going to be printed. So after printing, whether my structures are going to come out the way I wanted. Okay, so you do those proximity correction, and then after correcting the data, you check it with design intent, right? So you have extracted the timing and everything, right? So you are going to do all these extractions again of the proximity corrected circuit. So design is one thing, right? But then now you have corrected for the optical proximity, right? So after correction, whether my circuit will still yield same performance or not, right? So that is what you will do by supplying this design intent data to your corrected layout. And this correction is done by using your lithography details, right? So you will have lithography rule check after that, and then you have the mask data and then your mask inspection data. All these things are there. So this control data is nothing but your process data. So I am going to do some lithography process, and this is my limitation of my lithography process. So I feed those data for optical proximity correction. I feed the same data for rule check as well, for data prep, and also mask inspection. So now your process is very involved, because you are involving how my device is going to look like after fabrication. So if this is what my process specifications are, whether my current design will yield desired circuit or not is going to be checked even before you make the mask. Okay, that is the beauty of this whole process flow. It is very involved, but you will get a better circuitry both in terms of yield and reliability. So after doing optical proximity correction, you do lithography rule check, right? So this is again a kind of design rule check, but in this case this involves also projection simulations as well. So once this litho rule check is done, you do mask preparation, right? So you prepare the data for mask writing, which is something we saw earlier. This is a writing process. So we need to find what are all the places that we want chromium, and what are all the places we want the mask to be transparent. All those things are prepared. So once it is prepared, we make the mask, right? This is mask making. So once the mask is made, we do inspection, which is again a very important step. So inspection allows you to find defects. So if there are any defects, then what we do this again, right? So these defects could be corrected. So there are two type of defects. Again, one is a random defect that could happen because of process variation or some process failure during mask fabrication, or this could be from data preparation itself. So if the data prep was not clear, and if you are getting some systematic failure in your mask writing, then you go back to your mask data preparation, and then you fix that problem before making the mask. And once all of this is done, then you take the mask out, okay, for further fabrication. So this process is very involved, right? And some of this process is taken care by the designer. Till here is done by designer, and then after this, this is all taken care by the lithography team, let's say, okay, that is going to take care of corrections and so on. But the interface here is this design intent, right? So what is the purpose of my circuit, right? So you share this detail with the litho team, and they are going to use those data in order to do the timing analysis after doing proximity correction, or in some cases it is given back to the designer to run the timing analysis and also window and so on. So it is very important that there is a closed communication between the designer and your mask preparation team, that you get your desired circuits fabricated that will yield the required parametric performance as well, not just the structural yield, right? So you may just have a line, right, but then whether the line is of required resistivity, right, if you are going to look at the timing. And in order to do this, it takes a lot of effort, right, that we saw earlier. So these efforts cost resource, right? And when I say resource, this is human resource and also other engineering resource, and you have to spend some cost on this. This can be hard cash, or this can be time, right? And there are two type of expenses that you have in a product. One is recurring engineering cost, and the other one is non-recurring engineering cost. So if you look at recurring engineering cost, it is very hard to completely avoid recurring engineering costs. You try to reduce it, but it will be there, but you can actually try to reduce it, right? But there is non-recurring engineering costs, which is something that one can completely avoid going from one product to the other product, right? So the way that one can do this is you have a product or a device D1, and then if you are going to device D2, if you are going to share majority of layers and structures that you have developed for device 1 for device 2 in terms of layout, right? Let's not worry about if I have a gate thickness variation between D1 and D2, this is not going to affect too much of your layout, right? If the line widths are maintained, then you are okay. So there are few design parameters that you can still keep unchanged going from one generation to other generation, right? So this may be related to one generation of node to other, but primarily same node, but you are doing different functionality, right? So if that is the case, then you may want to have a good compatibility between different device generations so that you can avoid engineering cost, okay? And the way to also reduce your engineering cost is by doing multiple tests on a single wafer, right? So this is one wafer. So one can divide this into 4 quadrants, right? So you can have prototype for device A or product A, and I'm going to do product B and product C as well, and there is some short loop I'm going to run to check some functionalities for product D, right? So this is how you can reduce your non-recurring engineering costs, because you don't want to waste the full wafer for just for development or proof of concept of a particular prototype. So prototypes can be always shared, and this can be done by using lithography process, right? So in optical lithography, you can designate different space for different devices so that you only use part of it, but the processing is going to be the same. So litho process, etch process, metallization, this is all going to be same, right? But your circuits are slightly different, so you're sharing the process, yet you are getting 4 different type of experiments done on a single wafer. So this is how you reduce your non-recurring engineering. So with that, we understood how just lithography alone, right, can be very helpful in DFM. So there are each and every unit process could contribute towards DFM in this way, where you are closely looking at the process variation and then using those process knowledge to make the devices and circuits yield better, right? So with this, we would like to say that design for manufacturability is very specific, right? It's very detailed, like what we saw in lithography just alone. The same could be applied for multiple process steps as well. So in the next lecture, we will see how we can use the DFM, right, for doing backend and so on.